Alright, so we're starting our set of notes here in counting and probability. Alright, so counting and probability starts with first just basic understanding of set notation and set operators. Alright, so this is sort of the first video. Hopefully you've got a copy of the guided notes that are on ReggieNet in front of you. It will really make following this video a lot easier. It'll also make it easier if you go back and look at the notes where you filled in the guided answers from this video. Also, some of this stuff is basic and you may have seen it before. Try to answer before I do. Alright, see if you know the material and answer before I do. Always a good idea to see if you can do that. Alright, so chapter 6 is a big chapter. We start with chapter 6. The first 8 weeks of the semester we're going to start with 6, 7, and 8, right, which are your first 3 quizzes, over counting, probability, and statistics, and it really builds off of itself. And so we start with chapter 6, which is counting. Right? You have to be able to count stuff before you can do probability and statistics with it. Alright, so this counting chapter is very, very important. Very, 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 very important. We will basically be building off of this chapters for the first half of the semester. Alright, and so make sure you've got this stuff down. Alright, so we start off with the first set of notes, definition and notation for sets. Alright, so set is basically just a well-defined, there's that kind of highlighted, well-defined collection of objects. Alright, and the objects can be people, items, things, ideas. Alright, they can be any of those things. So a simple example would be, alright, suppose we deal a lot with numbers, right? Suppose set A is the set of all positive, read my handwriting, alright, positive integers less than 11. Alright, so set A is the set of all, so there's my definition, my well-defined, my objects are positive integers that are smaller than 11. Alright, so now I'm going to list them. Alright, so positive means bigger than 0, integer means the whole number values, no fractions or decimals, and less than 11. So 1 through 10. Alright, there's the set of all positive integers less than 11. Positive bigger than 0, integer means whole number, less than 11, so well-defined collection of objects. Alright, well suppose, we're going to do experiments later on. Suppose set B represents an experiment. Set B is the outcomes, all outcomes, when I flip a fair coin. Alright, so set B, there are only 2 possible outcomes when you flip a fair coin. You can either get heads or tails. Alright, and that's all the possibility. Another set which I can't list would be, suppose I wanted to survey all freshmen coming into ISU this fall. Alright, well, the list would be, somewhere there would be a master list with the names of all freshmen on it. Alright, that would be the collection of objects. Or all math majors at Illinois State University, and so on. So again, collection of objects can be numbers, experiments, right, and people. Alright, an element. An element is an object from a set. Alright, the notation is a little weird. Mathematics is a language. We use our own names and our own notation for stuff, and we love to shorthand things. Alright, so I'm going to put a different set A down here. I'm going to say set A is the numbers 2, 4, 6, 8, and 10. Alright, so the even numbers from our previous set. Alright, so 2 is an element from set A. Right? 2 is a number as an element from set A. And so what we do in mathematics, we shorthand. Instead of writing this phrase out, 2 is an element of set A or 8 is an element of set A, we've got this notation. Alright, kind of looks like a backwards E. And again, you'll have to bear with my handwriting on my tablet here. Alright, that symbol stands for element from set A. So it says the exact same things, just using math symbols. Alright, so 2 is an element of set A. 10 is an element of set A. 6 is an element of set A. Alright, and so that symbol represents the phrase element of in mathematics. And it's used mostly when we do definitions and things, but you should be aware if you see it written somewhere, right, you know what that symbol means. Alright, element of. Alright, set B is equal to set A, and we denote it with the equal sign if set B and A contain the same element. So I'm going to use the same set A I had in the previous example. Alright, the numbers 2, 4, 6, 8, and 10. Alright, set B supposes the set 8, 4, 2, 10, and 6. Alright, in order for my set A to be equal to my set B, they have to contain the same elements. Now, B is written in a slightly different order, but it doesn't matter as long as they have the same elements. It's got 2, 4, 6, 8, and 10. And so B is equal to A. Right, B is the same as A. Right, they're equivalent as long as they contain the same elements, whether they're reordered or not. Alright, subsets. So we're going to be dealing a lot with subsets. We're going to be finding subsets of groups and being able to count subsets of groups. So it's very important that you understand what a subset is. Alright, so general subset. Alright, so we've got set B and we've got set A. Alright, set B is a subset of A if every element in B is also an element in A. Alright, and so the notation for subset that you have to recognize is this notation, sort of like a sideways U. Alright, B is a subset of A. Alright, so I'm going to use the same A and B I had before. So 2, 4, 6, 8, 10. I'm going to do the same B I had before. I might write it in a slightly different order, but as long as, again, same elements. 2, 4, 6, 8, 10. Alright. And I forgot a very important part of my subset. There should be a little line underneath this symbol. Alright, because a general subset allows for equality. Alright, so there should be a U symbol with a line underneath it. And then this is true. Alright, every element in B is also an element of set A. So if you check, every element in B is also an element of set A. Alright, I'm going to add another set here, set C. Set C is the set 2 and 10. Well, C is also a subset of A, right? Because every element in C is also an element of A. Now, C has fewer elements, right? But the definition still holds. Every element that's in my subset C is an element of my big set A. It's also, C is also an element of B, a subset of B, right? Every element in C is also a subset of B. Alright, so as I do D, is just the set 6. Alright, well D is also a subset of A. D is also a subset of B. Alright, every element in D is in A. Every element in D, there's only one element in D, and it shows up in both A and B. Alright, so that's the subset. Alright, so subset allows for equality. That's what that little line that I actually forgot at the beginning there. So that little line means they could be equal to, right? B equals A. Well, equality and subset are okay, right? Because that line allows for equality. The next definition, we're going to throw that out. Alright, set B is a proper subset of A if every element in set B is also an element of set A. So that's the exact same as our previous definition, but then we've added this last part. Equality is not allowed. Alright, A has to have more elements than set B. And so it's actually the first way I wrote it. Drop the bar on it. It's kind of like the inequality notation, less than or less than and equal to. Same thing here. Alright, without the bar underneath there means set A cannot be equal to set B. Alright, and so I'm going to do the same set A, but I'm going to put a different set B here in order not to be equal to. So set A was 2, 4, 6, 8, 10. Set B is 4 and 8. Alright, and now set B is a subset of A. Alright, suppose I do another set C which would be 6 and 10. Let's do, instead of 2, let's do 3. 6, 10, and 2. Alright, subset C is a subset of A, right? Every element in C shows up in A, and C is not equal to A. A has more elements than C. Let's suppose D is the subset 4. Alright, so D would be a subset of A. D is also a subset of B, right? Every element in D shows up in B, right? 4 is an element of D, 4 is an element of B, and B has more elements than it. Same thing for A, right? 4 is an element of D, 4 is an element of A, and A has more elements than it, alright? So this is what we mean by a proper subset does not allow equal to. Going back here, a general subset does allow equal to. Alright, so we put the little bar, we're allowed to have sets that are equal. Without the bar, we're not allowed to have sets that are equal. Alright, next rule or definition. The empty set. Alright, the empty set should be sort of one of those, yeah, it makes sense. Empty set basically is a set containing no elements. Alright, in mathematics we have the empty set. Alright, the empty set contains no elements, and the empty set is always a subset of the other sets. Alright, so the notation for the empty set is a circle with a line through it. Remember, that's the same as saying no solution, right? Which is why we have an empty set in mathematics. An answer to sometimes some mathematical questions is no solution, right? The solution set is empty, right? There is no answer that works, therefore it's an empty set. Alright, and so that symbol is this circle with a line through it. Alright, that means the empty set, there's no solution to the problem. Alright, the empty set is always a subset of another set. Alright, and it can be a general subset or a proper subset. Nothing, it should make sense. Nothing is always a subset of something. Right? Nothing is always a subset. It's one of those weird things, but it's always true. Alright, nothing is always a subset of something. Alright, last thing from this page is the universal set. Alright, we'll be talking about universal sets and sample spaces when we get to experiments. And so that's why a lot of times capital S and capital U's are used for what's called the universal set. The universal set is basically the set where we're looking at all of the elements under consideration. Alright, so suppose my first example was I want all of the elements under consideration are the real number values. Alright, that would be my universal set. Or all freshmen at Illinois State University this fall. That would be my universal set. And a lot of times we'll use capital S or capital U. The reason why capital S is used is when we get to experiments, we often use the phrase sample space. We do an experiment like flipping a coin. Alright, the sample space is all of the things that can happen in my experiment. Well, my sample space would be I could get heads or tails. Alright, and so that's the universal set, all elements under consideration in my experiment, or in my group that I'm looking at. Alright, so first example is just practicing understanding when I have a proper subset, universal set, or equal sets. Alright, so again, hopefully you can answer these before I do. Alright, that's the idea. Alright, so I've got S, which this is my universal set. Alright, so set S is my universal. Meaning I'm only interested in the integer values 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't care about any other numbers. Alright, those are the 9 numbers I'm looking at. Alright, that's my big set, my universal set. Alright, the rest of these, E, A, B, C, D, should all be subsets of that universal set. Alright, so we want to determine if the following sets are true. Alright, so determining if I've got subsets or proper subsets. Alright, so the first one is D, a subset of A. Well, A is the numbers 2, 4, 6, 8. D is the numbers 4 and 7. Alright, are every element in D in A? Well, no, that's false because 7 shows up in D and 7 does not show up in A. And so that's false. Alright, not true. Alright, is B a subset of S? Well, I said it was, but you should double check and make sure I'm correct in that statement. Alright, so the B is the numbers 3, 4, 7, and 8. Alright, is every element of B in S? Well, 3 is in S, 4 is in S, 7 is S, 8 is in S, so that's true. Alright, empty set, right? That symbol stands for the empty set, a subset of C. Well, remember, the empty set is always a subset, alright? Nothing is always a subset of something. Alright, so the next three involve set A and E, right? D, E, and F involve my set A and my set E. And so if I go back here and I look at my set E, it's a written description instead of a list of what it represents. Alright, so here's A. A is the 2, 4, 6, 8. E is the set, where n is my number. Alright, n, so every n, such that n is a positive even integer less than 10. And so I'm going to list set E. Alright, so set E are all the positive, meaning greater than 0, even, so even numbers only, that are smaller than 10. Well, what are all the positive even integers less than 10? Well, 2, 4, 6, and 8, right? 2, 4, 6, and 8 are all my positive numbers, whole numbers, less than 10. Alright, so there's set E, alright, there's set A, and so the first question was, is set E equal to set A? And yeah, once I've listed it out, I can see A represents all of the even integers less than 10, so that's true. Alright, well the next one's asking for, is A general subset of E? Alright, well, because they're equal to, the previous statement says they're equal. That little bar underneath the subset says equality can be held true, and so that's true. Alright, A is a general subset of E. All the elements in A also show up in E, and I'm allowed equality. Alright, the next one, is a proper subset of E. Remember, to be a proper subset, every element in A has to be in E, which that part's true, but it's the second part that's false in this case. A cannot be equal to E. Well, they are equal, and so that makes this statement false. Alright, the next one involves B and D. Alright, so I'm done with set E and A. Now I'm just looking at B and D. Alright, that's basically the rest of the questions here on this set. Alright, so B, is B a proper subset of D? Alright, well remember, every element of B has to be an element of D. Well, this one just easy to answer is false because B's got more elements, right? And so every element of B cannot be in D because it has more elements, and so that one's false. Alright, well what if I flip it around? Alright, now B is the bigger set, and D is the subset. Alright, is D a proper subset of B? Well, two things have to be holding true. Every element of D has to show up in B, and they can't be equal. Well, D has the numbers 4 and 7. B also has the numbers 4 and 7, and they're not equal to because B's got 3 and 8 in it, and so that's true. Well, if you're a proper subset, you're a general subset, right? Because you hold on the subset case, all right? And so the general subset's also true, right? Every element in D is also an element of B. All right, because it's a proper subset, the last one's false, right? B and D are not the same, all right? So that's false. And so that's just practice. And again, hopefully you were able to answer all of those questions before I did. Alright, so again, that's just getting you used to, again, reading and writing using set notation. The biggest thing is being able to recognize it, alright, reading it, understand what it means, and when it's true and when it's false. Alright, the next video will be over Venn diagrams and set operators. Alright, on your own, practice this. Alright, so this is a practice one in your notes. Alright, later in the week or the next week, I'll post the key to these. Alright, and so this is one for you to try on your own. Alright, so on your own, see if you can't answer the following statements. Alright, using my universal set S, the subsets D, E, and F. Alright, so try if you can't answer those questions, are true or false, using the subset notation. Alright, and we will stop there.